All right. Hello, everyone. So welcome to our course on interferometric computational imaging. So we have three presenters, Alankar, Florian, and myself. Alankar and Florian, do you want to come by and say hi?
Hey, everyone, I'm Alankar. I was a PhD student with Ioannis, and now I'm a postdoc at the University of Texas Medical Branch and Rice University, and I work on computational imaging for neurosurgery. Florian?
Hi, everybody. My name is Florian Willomitzer. I'm an associate professor at the College of Optical Sciences at the University of Arizona. And we in my lab, we are working on developing novel computational 3D imaging methods that can be used in a broad range of applications, like, for example, medical imaging, autonomous driving, AR, VR, and so on. And one thing that we are especially interested in our research is how to utilize fundamental physical and information theoretical limits to build better computational 3D imaging systems. And I think we will tell you a little bit about this today as well.
All right. And I'm Ioannis Gkioulekas. I'm also an associate professor at Carnegie Mellon University, and I do a lot of research with my group on computational imaging techniques for problems such as 3D sensing, medical imaging, and so on. And also, in another part of SIGGRAPH, I'm doing a lot of research in physics-based rendering, in part because I like to use rendering to design optical systems. All right, so today's course is about interferometry. And I wanted to start with some examples of interferometric techniques that you may have seen around you, you may have experienced in your everyday life or read about in the news, just to give you an idea of the kinds of techniques or the kinds of applications that our techniques will be targeting. And I wanted to start with this one, which apparently, according to the Washington Post, there should be some experience that's pretty familiar to a lot of people doing computer science. So if you're wearing glasses or contacts or had laser corrective surgery, then you may have, during one of the visits to your optometrist or your physician, done an OCT eye exam. So this is a device where you go and look inside it. It looks like a white box like that. And really what this white box is an optical coherence tomography system. So it's a very nicely engineered and packaged interferometric system. And what it's used for is to do retinal scanning and angiography. Basically, your optometrist or doctor, by looking inside this device, they can see a tomographic scan of your retina, the layer of tissue that's at the back of your eye. And that's sensitive to light, and they can use that to diagnose different conditions such as glaucoma, diabetic retinopathy, macular degeneration, and a lot of other stuff that I hope we don't have to go through during our visits to optometrists. So that's one clinical application of optical coherence tomography that's very mature. And in general, interferometric techniques, not just optical coherence tomography, OCT, but many other variations of interferometric techniques have found a lot of applications in medical imaging, or they are being researched on so that because of their potential for medical imaging. For example, there is currently a lot of work at the preclinical level on using optical coherence tomography and interferometric imaging techniques for tissue imaging and skin cancer diagnosis. So these are some images here of breast tumors where, again, using interferometric imaging, we can do tomographic reconstruction about 2 millimeters below skin and use that to non-invasively diagnose whether someone has a tumor, whether there is a need for biopsy, and so on. And in fact, all of these applications are in medical imaging. A lot of the results we will show you today, and a lot of the new techniques and new development we'll show you today, are themselves part of a large expedition, NSF expeditions project that's trying to push the envelope in terms of what we can do with interferometric imaging, trying to use more advanced and more developed techniques that allow us to image deeper and deeper and deeper inside tissue, and in particular do so at micrometer resolution so that we can image features such as small tumors, maybe some blood flow details, and so on. So all of these are problems that interferometry has found applications on, that we are also working in, and that you are going to see some details behind the techniques underlying these applications. Besides medical imaging, another very common application of interferometric imaging is in 3D sensing. So nowadays, especially in autonomous vehicle applications, but also in other 3D scanning applications, you may have seen the term FMCW LiDAR. So this stands for Frequency Modulated Continuous Wave LiDAR, which is effectively a new term for a very classical interferometric technique called swept source optical coherence tomography. And this is a LiDAR technology that's used to give us both depth and velocity through the Doppler effect for scenes that can be either at the level of room scale or like a road scale or maybe even very close up. And it has a few advantages over regular LiDAR, such as it can reach very large ranges. And of course, as I mentioned, it can do both depth and velocity, which is why it's sometimes called 4D LiDAR. And in general, we have a lot of applications of interferometry in 3D sensing, not just in the context of LiDAR, but also, as Alankar will show earlier, in the context of micrometer 3D sensing, very, very high resolution 3D sensing. For example, for applications in inspection, when like an aircraft lands or when an aircraft goes into maintenance, engineers want to check the different sections of the aircraft for different defects, different indentations that may have happened because of collisions, and which can cause risks. So all of these require being able to inspect the shape of this aircraft very quickly and also at very, very high resolution. So these are scans in this case in a resolution of 5 micrometers. Or alternatively, for quality control in fabrication, you can, people use interferometric 3D imaging techniques to be able to tell how accurately a fabricated object conforms to specifications, how closely it matches the design you provided to a 3D printer, or maybe even during the 3D printing process to give some feedback to the printer about how to correct for mistakes that have happened during the printing process. So medical imaging, 3D sensing. I'm going to also show one more application area of interferometry. It's going to be a bit outside of what we cover in this course in terms of infrastructure, but which has the same physics and the same optical techniques underlying this kind of research. This is in very large-scale physics. And what do I mean by that? I mean kilometer-long interferometers, like at the Hanford lab in Washington, at the LIGO project that was used to detect the first gravitational waves, or even Earth-sized interferometers for very large baseline interferometry, like the Event Horizon Telescope that was used to capture the first image of a black hole. All right, so both of these techniques are interferometric techniques, so a lot of the background we'll go over today also applies, again, at very different scales, but same physics to these kinds of techniques, though, as I mentioned, you will not really see much results or much technical exposition from us about these kinds of techniques. What we will focus on instead is the use of interferometry for computational imaging applications, basically kinds of imaging modalities, imaging capabilities that are well outside what a conventional camera can do, such as non-line-of-sight imaging, light in flight and transient imaging, separation of direct and indirect illumination, and so on. Okay? So both Florian, Alankar, and myself will all go over a few examples and a few results of applications such as this. So here is an overview of the course. We'll start with a quick introduction to interferometry, some very basic material. Then Florian will take over and discuss two-wavelength interferometry, how we can adapt some of the stuff I will show to the case where we use illumination that has very specific spectral properties, in particular comprises two wavelengths. Alankar will take on and show how to generalize this result to the case where we're using partially coherent light that can be doesn't have to come from a laser, but it can come from an LED source, and it can have arbitrary spectrum and so on. And finally, Florian and I will close with some discussion of computational imaging techniques using interferometry. So I'll start with this. Let me say one more thing, that at the end we're going to have a Q&A, so if you have any questions, please take note of them, and you're welcome to ask them towards the end of the course. So let's start with an introduction. Again, I'll try to keep everything at a very basic level just to understand just the principles of what's behind interferometry and what we mean by interferometry. And for that, I'm going to show a schematic of a very simple setup, very classical and simple setup called the Michelson interferometer that looks like what I have over here. So what do we have here? We have some coherent light source. This can be a laser, can be other things. We'll describe a few different light sources throughout the course. that we use to create illumination for an optical system. We collimate it with a lens to create a collimated beam. We pass this through a beam splitter. A beam splitter, if you're not familiar with optics, is a device that lets half of the light pass through and reflects the other half at 90 degrees. So by doing that, we split our beam in two, and we use the beam to illuminate both the scene we want to image and also some other scene that we get to control. Typically, it will be a mirror that we can move along different locations. Light will reflect these two scenes at what we sometimes call the target arm and the reference arm, and we'll come back to the beam splitter, we'll recombine. And then the camera will see the combination of the light that's reflected from the reference arm and the target arm. Now, what will the camera see? The camera will see, if the camera was observing just the scene arm, obviously it would see just an image of the scene. If we were observing just the reference mirror, it would see just an image of the reference mirror. When it's observing both, it will see an image that's the summation of those two, but also some extra component that comes from the fact that we took a beam, we split it in half, and we recombined it. So because of constructive and destructive interference, we'll see that our camera will have some additional signals, some additional measurements, which we call, because of the interference of these two waves. And because this interference is exactly what we measure, hence the name interferometry, measurement of interference, all right? Now, what this interference will look like, what information we can extract from it, will depend very strongly on what type of light source we use and what kind of reference arm configuration we use, the mirror or something else. And again, throughout the presentation today, we'll go over a few different settings for both the light source and the reference arm, and also the associated information in the interference signal. Now, the design I've shown here is one of the most basic interferometer designs called the Michelson interferometer, but there are a lot of other optical setups, all of which go along the lines of split a beam, use it to illuminate two scenes, and then recombine them. You can do that with very many different configurations. For example, another very common one is the Mach-Zehnder interferometer, where we now use two beam splitters, one to first split the beam, reflect, and then another to recombine and send it to the camera. And depending on your application, you may also see a lot of other interferometer designs like Sagnac, Fizeau, Searing, and so on. I'll use the Michelson interferometer in this introduction as my go-to example for like an interferometric setup, but again, a lot of the things we discuss apply to all of these other types of interferometers. In addition to the design, the paths that light is gonna follow after being split and after being recombined, we also have two core choices of implementation. There are full field interferometers, where we use a 2D sensor, basically a regular camera, and free space optics, large mirrors, large beam splitters, and so on, so that we can simultaneously illuminate all of our scene and simultaneously image all of our scene. But we can also do fiber-based interferometers, where instead of light traveling in free space, it now travels inside fibers. We replace beam splitters with fiber splitters, and we only illuminate, we don't have a 2D sensor, we have a photodetector, a single pixel sensor, and now we're only illuminating a small part of our scene. And in this case, in order to be able to form a 2D image, we need to raster scan and sequentially illuminate different parts of our scene. And again, here in the fiber space or in the scanning mode interferometry design space, there are a lot of design choices. People use circulators, balanced photodetectors to increase SNR, and so on. Details that we won't go through so much. We will primarily stick with the free space Michelson interferometer as our go-to example for like a standard interferometer design. Alankar will discuss a little bit more about pros and cons of fiber-based versus free space implementations. All right? So the last thing I wanted to go over in this introduction is give you an example of what kind of interferometric signal we can measure for a specific type of light source and a specific type of reference and scene configurations. And in fact, this is probably one of the simplest interferometric experiments that someone can do that goes by the name phase shifting interferometry. So in this case, we make our light source be a single frequency laser. Now, you may think that all lasers are monochromatic. This is true to some extent or another, but here we're talking about lasers that have really very, 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 very narrow emission spectrum, like something in the order of 10 to the minus 3 or 10 to the minus 6 nanometers, all right? Very narrow single frequency lasers. And we'll replace our scene with a very simple scene in the form of a tilted mirror, okay? Now, if I had a way to go and look at the wave that's propagating along the x-axis, the optical axis of the interferometer, right after the source, I would see, because light is a wave optical effect, I would see a sinusoid. A sinusoid whose period is equal to the wavelength of the laser, like let's say 500 nanometers for a green laser. This splits in two, so I will have another sinusoid travel towards the reference mirror and another travel towards the tilted mirror. This will recombine, and then the two waves that will reach the camera will be, again, two reflected copies of these two sinusoids. These copies will have a tiny phase difference. And the reason for this phase difference is that the wave that went into the reference mirror and the wave that went into the tilted mirror, they had to travel a different distance. And in fact, this difference in distance will be different for different pixels, for different locations of the tilted mirror. So this phase difference is going to be proportional to the distance, the difference between the propagation distances, modulo lambda. Because wavelength is sinusoidal, we need to remove as many wavelengths as possible from this difference. Now, what does the camera measure? The camera, or rather the interference part of the camera measure, will be nothing else but the correlation of these two sinusoids. And because we're correlating sinusoids that have the same frequency, the same wavelength, the correlation itself will be another sinusoid of the same frequency, of the same wavelength. And in this case, we're going to take an intensity measurement. It will be some point on this sinusoid, with the exact point depending on the phase difference between the two reference arms. So how do we measure this phase difference? How can we figure out the phase that corresponds to our interferometric measurement? What we can do, and because of this, because for different pixels on the mirror, we'll have different phase differences, what we'll see is an interferometric image that looks like this. Effectively, we're seeing at white parts, places where the phase difference is 0, so the reference arm and the mirror arm have sinusoids that exactly overlap and we have constructive interference, and places where we have 0 intensity, meaning that the phase difference between the reference arm and the scene arm is half a period, and we have a destructive interference, all right? Now, at every pixel, we want to measure exactly this phase difference, because we can then translate that into depth, effectively how different the propagation in the reference arm is compared to the target arm. And we can do that using a technique called phase shifting, hence the name phase shifting interferometry. So what we do in this case is we take the reference mirror, we place it in a very accurate translation stage, and we capture measurements at 4 different shifts, at maybe 3, usually 4 different shifts of this mirror. The shifts are in the order of quarter wavelengths. And then we're going to capture 4 different interferometric measurements corresponding to 4 different phase shifts. From those, we can run some simple math that go by the name of phase retrieval algorithms to extract the depth, or at least the depth up to a single wavelength of the point in the scene that the current pixel is imaging. So here is an example of this. Phase shifting interferometry is used to do surface deflectometry for very smooth optics where we really care about accurate shape and also any imperfections. For example, lenses that we try to manufacture at an accuracy of quarter wavelength or very well-designed mirrors and so on. So in that case, we can use as our reference shape not a planar mirror, but the actual shape we want to image, and as a test shape, the mirror or the lens we have fabricated. And then by doing phase shifting interferometry, we can measure the exact shape, or at least the exact deviation of the test shape from the accurate one, and we'll see an image like that that shows us both the spatial variation in the mismatch between the test shape and the regular shape, and also we can capture a phase map that will give us more quantitative measurements of these phase variations. So phase shifting interferometry, very simple technique to do depth imaging at sub-wavelength resolution. But it comes with a lot of caveats. Outside of optical testing, it's generally not a technique that is incredibly helpful because the depth range is just 1 wavelength. Beyond 1 wavelength, I have phase-wrapped measurements. I run into another period of my sinus, and therefore I cannot tell unambiguously what my depth is. It only works for very smooth surfaces. All of the examples I've been showing so far have been mirrors, glasses, and so on. It's very sensitive to vibrations, given that we are imaging at a resolution of quarter of wavelength. Even things like airflow in the room, people moving around and so on, can really mess up with our measurements. And it's also very sensitive to optical aberrations, like your lens having some imperfections and so on. So a nice technique, conceptually also a good way to introduce interferometry, but not really something very practical for 3D sensing, at least at the levels of everyday room scale or object size or city size depth sensing. So I'm going to pause here with my quick introduction to interferometry, and I'll hand it over to Florian, who will go over ways to deal with some of these issues using two-wavelength interferometry.
Okay, yeah, great. Thank you, Ioannis, for this very nice introduction. So before I start, I would actually like to emphasize that all work that I'm presenting you today from our lab has, of course, not been done by myself alone. This is, of course, also the work of many, many students and collaborators, and I would like to take this opportunity here first to thank my current group members for their very hard work, especially the ones here in the red box who directly contributed to the work that I'm showing you today. And of course, I would also like to thank our collaborators and previous lab members who have also contributed to this work that I'm showing you today. Okay, so in the last 20 minutes or so, we have learned about the coherence properties of light. And we have also seen that these properties, they can be exploited to measure distances or optical path length differences. And the devices that we use for this, they are commonly referred to as interferometers. One very important thing, as Ioannis was saying, everything what has been discussed so far, this was for the measurement of smooth surfaces, like mirror-like metal surfaces or polished glass surfaces of lenses. And indeed, measuring such surfaces with very high precision, this is indeed one of the main applications of interferometry. So for example, in optical metrology or industrial inspection. So now we're going to talk a little bit about interferometry on rough surfaces. And many people in the audience might already know, so for example, from graphics rendering, that there is actually a fundamental difference how light interacts with smooth surfaces or rough surfaces. And it actually turns out that this difference is even more prominent in coherent imaging and actually leads to a couple of very interesting problems for interferometry. And I will also present you some solutions to this today, which are based on so-called synthetic wavelengths. Okay, so let's see what happens if we illuminate a rough surface with coherent light. In this case, let's say we have a plane wave with wavelength lambda. What happens now is that the light hits the rough surface, and then it is backscattered now from different depths of the surface. So in other words, what happens is every point here on the rough surface is basically the origin of a new wavelet, and all these waves propagate in space and then they interfere with each other. And this process is totally chaotic and random. And then in the space after the rough surface, we have interference maxima and minima forming. And the 3D shape of these maxima and minima, this looks a little bit like little cigars, little cigar-shaped objects. And this is called speckle, or in this case, objective speckle, and the respective field is called a speckle field. And if we would place a detector here, so for example, a camera chip, what we do is basically we image a cross-section of this speckle field here, and this looks like this. So if you look closely at this, this actually looks a little bit like noise, and this is also the reason why many people refer to it as so-called speckle noise, but it is actually fundamentally different from the other noise that we know, for example, photon noise. And to understand this, we can now directly look a little bit on what our camera really sees when we image a rough surface with coherent light. So let's say we illuminate this cluster figure here with a laser, and then we take an image of this with a camera. If we look at the amplitude of the image, we see again this characteristic speckle pattern here that we already know. And let's say if we would only be interested in like taking a very nice 2D image of the object, then indeed some image filtering might indeed help to mitigate this speckle effect a little bit. But remember, what we want to do now is we want to acquire range information via interferometry. So let's pretend our camera is an interferometer, and let's look at the respective phase map. And as you can see here, the phase map of such a speckle pattern, this looks very, very different from these clear phase maps that you might know from smooth surfaces and that we have seen before. It's actually completely scrambled, completely all over the place. As you can see, it varies very quickly here between 0 and 2 pi. And this basically means that I can get no range information out of this phase map. And this is a problem. So let's dive a little deeper into this to understand what is really happening here in a very simplified picture. So let's look again at our rough surface here, and let's zoom into the rough surface until the level of 1 spatial resolution cell of our imaging device. And now let's assume that the rough surface still varies significantly within this resolution cell. So now we illuminate this with a coherent plane wave. And this basically means that all these purple maxima, they form a planar wavefront. And then as soon as this wavefront hits the surface, it actually catches up this path length variation psi here. And this happens now for the incoming and the outgoing beam path. And you can see now that for the outgoing beam path, these two maxima are offset with respect to each other by 2 psi. And this means that there is some destructive interference happening here. And in this example, the offset is already multiple wavelengths long. But you can also formulate a limit case for this, and you can basically say a limit that says exactly when the first completely destructive interference is happening, or in other words, when you will see your first dark speckle in your image. And this is when the path length variation or the path length difference 2 psi that I was picking up here exceeds lambda over 2. And this means that maximum and minimum of the two overlapping outgoing waves exactly line up and cancel each other out. So using this formula now, you can basically say that you get speckle-free imaging if the maximal path length variation psi within a resolution cell is smaller than lambda over 4. And this is indeed one of the definitions that you get speckle-free imaging if the path length variation is smaller than lambda over 4, and you see speckle when the path length variation is larger than lambda over 4. And indeed, this is a definition that you can use to distinguish now if a surface is optically rough or not. And I have to say this is of course, still a very simplified image here. There are also some statistics involved, but hopefully everybody gets the main point here. So, 2 important remarks that I have to say. First remark is this obviously depends on the resolution cell of our system. So surfaces that look rough for a mobile phone camera, for example, they might not look rough under a microscope objective. And second important point is, and this is very important, this also depends on the wavelengths. So surfaces look less rough or not rough at all for larger wavelengths. And this is a possible way out of our speckle dilemma. So if we look again at the spectrum of approaches that measure the time of flight of light, we have seen conventional interferometry here on one end, and as Ioannis was saying, this works with optical waves up to micrometers, and we have seen that standard interferometry does not work on rough surfaces because of speckle. Some of you in the audience might be familiar with so-called time of flight cameras. And these time-of-flight cameras, they use very similar ideas to measure path length differences, but in this case, the optical carrier frequency of the time-of-flight camera is actually amplitude, or the optical carrier is amplitude modulated with an additional frequency, and this produces a much larger wavelength of several tens of centimeters or even meters, and this larger modulation wavelength is then large enough to be insensitive to scattering. However, always when we talk about surface measurements, we always also need to take the depth resolution into account, and the depth resolution is always proportional to the modulation wavelengths of these time-of-flight principles. And this means that this very long modulation wavelengths of time-of-flight cameras, this may lead to resolutions which are not sufficient for many applications. So think, for example, of medical imaging, where you have, where you might want to image structures which are like much, much smaller than 1 millimeter, for example. And the problem is with these time-of-flight modulation wavelengths that they cannot be further reduced because of limitations in silicon manufacturing technology. So from this picture here, it actually looks like the sweet spot is somewhere in the middle, right? And what a surprise. This is exactly where all these principles that are using synthetic wavelengths interferometry or dual wavelengths interferometry operate. So in other words, what we want to have is we want to have millimeter-sized wavelengths, but we still want to use optical light as a carrier because we have all these very nice high-resolution detectors for optical light. And yeah, let's take a step back and think a little bit about it. I mean, millimeter-sized waves with visible light. Is this even possible? And the first answer is no, of course not. But let's take a step back and look at a related example of sound waves. So what I will do now is I will play you now two sound sine waves with slightly different frequency. And this means they have slightly different wavelengths, as you can see here. So the first one has a wavelength of 1.429 meters, and this sounds like this. And here's the second one with 1.417 meters wavelengths, and this should sound slightly different. Maybe some of you can hear it. Again, the first one. Okay, and now when I play both of them together, something very, very interesting happens. It's not a computer trick, by the way, it's physics. So what happens is that these waves beat together and they form this new voom, 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 voom amplitude modulation, right? And this happens now at a wavelength that is actually much larger than the original two wavelengths. And it actually turns out that we can exploit exactly the same phenomenon, but now with optical light. So exactly the same thing, we overlap two lasers with slightly different wavelengths, and then we produce a high frequency wave with a low frequency beat node. And then with special detection methods, we are actually able to computationally or electronically isolate this beat wave, and this forms then the lower frequency synthetic wave. So two important things that we need to mention here. First is that the synthetic wavelengths can be freely chosen. It only depends on the two optical wavelengths that we choose. So in this case, it's exactly 1 millimeter here, which is much smaller than the modulation wavelengths of time-of-flight cameras. And the second important thing to say is that the carrier of the information is still the optical light. And again, this means that I can use fairly conventional detector architectures with very high pixel resolution, and also the reflectance of object surfaces that I measure is still the reflectance that I would see for optical light, which is very beneficial in many cases. And we can use this principle now to perform high-resolution time-of-flight measurements at this synthetic wavelengths. And this works now by putting both lasers at both wavelengths in an interferometer setup and then measure the backscattered speckle fields at each wavelength. And as I said before, the phase of each of these fields is completely scrambled and reveals no information about the macroscopic path length variations at all. But things change now if I take the two fields and form this synthetic field. And one way to do this is, for example, by computational calculating this correlation term, which contains the difference of the two phase maps, as you can see here. And this term is now particularly interesting because the phase of this term actually does show a clear structure and is not speckled, and this is exactly the phase map of the synthetic field. And what in fact is happening here is that the microscopic path length variations, they cancel each other out, and we are only left with the macroscopic path length variations, which are on the order of the synthetic wavelengths. Yeah, and here you see how the corresponding phase maps look like for measurements of real objects at different synthetic wavelengths here. And for the related depth maps of the object surface, we can easily achieve sub-millimeter depth resolution, and I will show some quantitative evaluations later. Before we go to the next topic, just a very quick side note. So this synthetic wavelengths principle that I just introduced, this is not only applicable to rough surfaces. In fact, it was already heavily used for decades in interferometric measurements of smooth surfaces or in transmission. So this is, for example, a transmission measurement where we measure the thickness of two glass plates here, and there is a mask in front of these glass plates with some digits, as you can see here. And if we look at the optical phase map, you see that the optical phase map is actually heavily wrapped, and unwrapping in this case is actually impossible because the digits are not connected, as you can see. And if we capture a second optical field and if we calculate the synthetic wavelengths term, then we can actually see that the phase map is now nicely unwrapped, and now we can clearly calculate the thickness of each of these glass plates here from the phase map. And whoever in the audience is maybe familiar with the term multi-frequency phase unwrapping, so this is also used in other disciplines in 3D imaging, for example. So for this example, forming the synthetic field is actually nothing else than interferometric multi-frequency phase unwrapping. And as I said, in these regimes, synthetic wavelengths have been already used for decades in many, many different fields. Okay, so by this time, we have hopefully convinced you that synthetic waves are pretty cool. But one question that everybody of you might ask yourself now is, if you want to use synthetic waves in your research, yeah, how would you actually detect the complex synthetic field or the two related complex optical fields that you need to calculate the synthetic field? And there are many, many different methods how you can do this. Some of them you already heard in the first part. Some of them will be also covered later. For example, you can do phase shifting, you can do temporal and spatial heterodyning, you can do phase retrieval, you can also do deep learning, just to name a few here. And to really dive into the technical details of each of these methods, we would probably need 2 or 3 additional SIGGRAPH courses. So unfortunately, we don't have time to do this today. But the very condensed message that I want to provide here is that this is obviously a vast play field, and every method comes with different benefits and drawbacks. So there's no free lunch. And this is the reason why I think that potential adopters of these principles, they should not immediately ask about the technicalities of each method. The much better question to ask, to my opinion, is what are the important modalities for my application? So for example, do I need a full field measurement, or is it sufficient that I have a point sensor and maybe raster scan the point sensor? Do I need to be motion robust or single shot in the very best case? Can I allow for a reference beam? Can I get away without assuming any priors about my object? Do I only want to use off-the-shelf CCD cameras or CMOS cameras? And so on and so forth. And in the last 5 minutes or so of this part, I would actually like to introduce you to an acquisition method that already checks many of these boxes that we see here. And this is our single-shot full-field acquisition with ordinary CMOS cameras. And this principle, this uses principles which are known from off-axis holography. So let's take a step back and see what we did so far. So we acquired these 2 optical speckle fields to calculate the synthetic field here on the right. And one thing that I did not emphasize too much so far is that the two optical speckle fields, they need to be correlated in order to make this work. So in other words, there's absolutely no motion allowed while these two fields are captured. And this is a big problem, obviously, for the measurement of dynamic objects. And later we will also talk about potential applications in non-line of sight imaging. So for example, imaging through fog or through tissue. And you can probably already imagine that the problem here gets even worse, because in these applications, for example, the fog particles itself, they might be in constant motion. So this is obviously a severe problem. And what we did to solve this problem is we developed a procedure to acquire the complete synthetic field in single shot, meaning that we only need one camera image and no image sequence. And as I said before, we can use ordinary CCD or CMOS cameras for this. So in our example here, what we did, or what we do, is we image the object onto the camera chip. And then for the illumination, we have a fiber-based setup in this case with, again, two tunable lasers that we couple together to form an object beam which illuminates the object here. And now comes the gag. What we do is we leave the reference beams separated and we arrange them around the imaging lens so that they directly illuminate the camera chip at an angle. And in this particular case, they are arranged so that the reference beam at lambda 1 encloses an angle in the horizontal plane, and the reference beam at lambda 2 encloses an angle in the vertical plane. And this produces us then a single image of a speckle pattern, which is overlaid with crossed fringes, as you can see here. And in this case, the vertical fringes contain only information about the field at lambda 1, and the horizontal fringes contain only information about the field at lambda 2. And now we can separate both of these fields in the Fourier domain, and by that we can retrieve two complex optical fields via a procedure that is called single sideband demodulation. And what we do now is we simply use both optical fields again to form our synthetic wavelengths term and to calculate the unspeckled phase map of the object surface. So again, this means we can retrieve two complex optical fields which are necessary to form the synthetic wavelengths term from only one single camera image. And this is then the result of this measurement. So here you see the wrapped and unwrapped phase map of the scattering object surface at a synthetic wavelength of 10 millimeters in this case here. And this is the resulting 3D model, which is shown from different perspectives. In this case with a depth precision of 1.8 millimeter. And I should also mention that we additionally developed a deep learning-based single-shot unwrapping algorithm so that we can unwrap these phase maps also in single-shot without acquiring an additional phase map. And as we have learned before, the depth precision also gets better with smaller synthetic wavelengths, which you can clearly see in this quantitative analysis here. So for the smallest synthetic wavelengths that we measure here, 1 millimeter, we achieved a depth precision in single shot of around 330 micron. And here on the bottom, you also see a visual comparison of the object measured at 50 millimeter synthetic wavelengths and 10 millimeter synthetic wavelengths. And of course, you can see much more details here on the right side. So again, this is all measured in single shot. But if your object is static, we can also relax this single shot requirement a little bit and still can acquire both fields sequentially in dual shot, and this commonly gives us a little less noise on our reconstruction. So this is another result from the measurement here of a clay pot, same field of view, but in this case smaller synthetic wavelengths of only 3 millimeters, and in this case we reached 800 micron depth precision. And here again is a comparison of the single shot and the dual shot operation, which are both taken at a synthetic wavelength of 10 millimeters. And you can actually see the slightly better noise characteristics here on the left side. Yeah, and last but not least, as I said, where the single shot capability really shines is, of course, if we do a video acquisition of moving objects. And this is what you will see on this slide here. So this object is a metronome with two attached letters. So the U is attached to the front and the N is attached to the bar of the metronome and basically moves around when the metronome is oscillating. And this is then the related 3D video that we get from this. So each video frame that you see here consists of an independently captured single-shot 3D model, and this can be now turned and watched in the computer from every perspective, basically like a hologram. Okay, and that's the end of my first part. Now I will give the mic to Alankar. Thank you very much.
All right, so we will now continue the trend of modifying our light source and spectrum, like Ioannis did with single wavelength interferometry, Florian did with dual wavelength interferometry. And as we modify the spectrum of our light source, we move on to what's called partially coherent light. To start off, we will consider the fiber-based interferometric systems that both Ioannis and Florian showed. And these are the ones that are most common in commercial use. As usual, these split light into two using a fiber splitter, one going to a reference and one going to a scene, and combine the reflected light at a detector. Using a broadband light source for interferometry results in a classic imaging technique called optical coherence tomography. Consider a scene point to which the path length from the splitter is d, with the reference arm placed at a position x, as opposed to the sinusoids that we have been looking at in the previous sections. The interference component is a very sharply peaked curve. The maximum of this interference component lies when d equals x. Intuitively, this happens because every single frequency in the spectrum interferes constructively at d equals x. It turns out that the combination of all of those wavelengths cancel out at most points, which are not equals x. The width of this peak, called the temporal coherence length, is inversely proportional to the bandwidth of the light. Since this form of OCT relies upon changing the time of flight of light in the reference arm, this is called time domain OCT. Then, if we place a sample, such as a retina at the back of our eye, as Ioannis suggested, on the scene arm and scan the reference arm, we measure interference signal from deeper and deeper inside tissue, effectively imaging its internal 3D structure. OCT has been used extensively for shallow soft tissue imaging in ophthalmology, cardiology, and neurology. Gradually, improvements were made to optical coherence tomography. A variant called frequency domain optical coherence tomography uses a spectrometer instead of an ordinary detector to measure the Fourier transform of this depth profile. The major advantage of frequency domain OCT over time domain OCT is eliminating the reference arm scan, and therefore resulting in a motion-free depth acquisition. As laser technology advanced, another variant of OCT appeared called swept source OCT, where a wavelength tunable laser is used with an ordinary detector to image the Fourier transform of the depth profile. This, as Ioannis alluded to earlier, is also the principle of operation of FMCW LiDAR. The image of the retina that I had shown in the previous slide was about 2 millimeters in lateral extent. This highlights a key disadvantage of fiber-based systems. For high lateral resolution, we need small fields of view for a reasonable acquisition time. Most commercial OCT systems take minutes to acquire centimeter scale scenes at micrometer scale resolutions. As opposed to this, CMOS cameras can easily image centimeter scale scenes and micron resolutions within one shot. So we move to the full field Michelson interferometer configuration that Ioannis had described. We place a broadband light source in the focal plane of the collimating lens in the Michelson interferometer to be able to move towards OCT. Consider imaging a toy cup, which is shown in the top left, about a centimeter in size with full field OCT. As we scan the reference arm, as before, the interference component shows sets of light paths that have increasing lengths. First, direct reflections from the sides, then along the bottom. After these direct light paths come the so-called indirect light paths caused by multiple light bounces in the scene. The direct light paths have lengths that are equal to the depth of the selected scene point that they are reflected from. We can use this property to also estimate a depth map of the scene by locating the peak of the direct-only paths. Here are some depth scans with exquisite lateral resolution acquired using full field OCT. So far, we have seen two different depth sensing technologies, optical coherence tomography and synthetic wavelength interferometry. SWI can also be done full field, similarly to OCT. Here are some major differences between the two. Firstly, the unambiguous depth range of OCT is constrained only by the translation limits of the translation stage or the frequency resolution of the spectrometer or wavelength tunable laser. As opposed to this, synthetic wavelength interferometry can measure unambiguous depths, not more than one synthetic wavelength without phase wrapping. The depth resolution of OCT is related to the spectral bandwidth of the source that's used, as opposed to SWI, where it depends on the separation between the two laser wavelengths. SWI offers the advantage of a trade-off between depth range and depth resolution by tuning this difference. OCT requires scene-dependent axial or lateral scanning, whereas SWI requires a fixed number of measurements, possibly just one, as Florian had shown before. Finally, the OCT scan allows for full tomography of the scene, as opposed to SWI, which can perform only surface-level imaging. Both of these methods can be done either fiber-based or full field. It appears that full field interferometry allows us to image at high resolution for free. However, there is a catch. To understand this, let's take a look at how images are formed by taking an example of the toy cup that we saw before. Consider illuminating and imaging this toy cup from the left. Among the set of light paths are direct light paths in green. These are the light paths that a fiber-based optical coherence tomography or a fiber-based interferometry system would pick up. This is because it illuminates and images just that one green point on the scene. However, when the entire of the scene is illuminated and imaged, a camera picks up contributions from paths like the red one, which are the so-called indirect light paths that come from other points in the scene. This multipath interference due to indirect light can cause depth reconstruction using interferometric measurements to completely fail. So, how do we capture the depths that we had shown before? To understand this, we need to understand the concept of light transport and probing. The interaction of light with the scene can be quantified in terms of light transport. To understand light transport, let us consider a scene that's illuminated and imaged from the left. For simplicity, we will discretize the light source and the camera into source elements and camera pixels. From a given source element S to a camera pixel C, light travels along a set of light paths. The sum of all of these paths result in an intensity ICS created by the source element S at the camera pixel C. These intensities can be stacked up into a matrix that's called the light transport matrix of the scene. The horizontal dimension in the light transport matrix corresponds to light source elements, and the vertical dimension corresponds to camera pixels. A conventional camera measures at every pixel the sum of the contributions of every single source element. This can be expressed by multiplying the entries of the light transport matrix by a vector of ones. A set of recently introduced techniques allow us to optically reject the contributions of subsets of light paths while imaging. These subsets of light paths are described in terms of their endpoints. This is an operation called probing. Probing can be mathematically represented as element-wise masking the entries of the light transport matrix by a probing matrix before forming the image at the camera. We perform this probing by replacing the point source in the focal plane of the collimating lens by an area source with a controllable amplitude profile. With this configuration, we can achieve arbitrary two-Blitz probing matrices, that is, matrices whose rows are shifts of a fixed pattern called the generator of the matrix. This fixed pattern is related to the Fourier transform of the amplitude profile of the light source. Using a large constant source in the focal plane of the collimating lens, we can perform separation of direct and indirect light paths using a diagonal probing matrix. This allows for the cancellation of multipath interference due to indirect light and allows for accurate depth reconstructions. Note how the specular reflections along the sides of the cup are gone in the direct-only image, along with a lot of subsurface scattering. We can use other two-dimensional light sources to perform anisotropic matched filtering. Consider this pattern, which is essentially two white stripes printed on a black background. We place the scattering slab on top of the pattern and image it with our interferometric setup. The presence of the scattering blurs the pattern to the point that it's no longer recognizable in a standard camera image. However, the interference component, upon using a horizontal light source, sharpens the white vertical edges, and a vertical source sharpens the black horizontal edges. Here is a picture of the prototype optical setup. The blue box is where the area light source resides, and the red box performs an additional phase modulation, which we describe in more detail in our paper in SIGGRAPH 2020. However, there is a problem with using an area light source with synthetic wavelength interferometry. As the size of an emitter increases, its spectrum typically broadens. We looked hard for a naturally available source. For instance, spectral lines on a sodium lamp or a laser with an area emission profile. Neither of these were monochromatic enough for our theory to hold. We also tried speckle reducers and built our own rotating diffuser, but neither succeeded in creating a satisfactory source. In addition, both of these were very light and efficient. Therefore, we emulate an area light source by time multiplexing the output of the lasers over the focal plane of the collimating lens. This results in a collection of plane waves that propagate at a small set of angles to the optical axis of the interferometer. Therefore, we call this swept angle illumination. Here are some depth reconstruction results on scenes around 1 millimeter in depth range. We compare reconstructions with and without swept angle illumination. The scenes cover a variety of material appearances, such as specular in the coins, scattering as in the soap, and highly diffuse as in the music box in the last row. In the last two cases, swept angle illumination improves depth reconstruction drastically by removing the contribution of a lot of indirect light. It also improves reconstruction quality for the coins, which are specular and have no scattering, just because swept angle illumination has been shown to mitigate the adverse effects of aberrations in full field optics. Here are some more millimeter scale results. The business card logo highlights the lateral resolution that full field interferometry can provide. To visualize this better, let's look at the synthetic wavelength interferometry depth rendered as a surface. We can see that the letters on the business card logo are reconstructed with exquisite lateral resolution. To really emphasize the capabilities of full field swept angle synthetic wavelength interferometry to measure high resolution depth, we reconstruct the eagle that's embossed on a United States $20 bill. The features on the bill are raised about 10 microns off the surface of the bill. Here is the recovered depth. Note how in the recovered depth, the spine lateral features, such as the gaps between the wings, are faithfully reconstructed with high lateral resolution. Here are some results on centimeter scale scenes that we can scan by tuning the separation between the two lasers. Indirect light constitutes a huge part of scene appearance for all of these scenes, and therefore we cannot achieve high quality reconstructions without the swept angle illumination. The speed up that swept angle SWI allows over OCT makes it practical to use for critical high resolution applications. We show here an example of inspection on an airplane fuselage section that Ioannis had previewed for a series of millimeter scale dents caused by collisions with atmospheric objects. Here, the recovered depths with and without swept angle scanning are shown, and without swept angle scanning, SWI is completely unusable for this application. This is another potential application, which is feedback during precision fabrication. Again, the ability to scan full field rapidly makes it practical to scan while fabricating. Here is an example of a translucent 3D printed coin pattern, and similar to the results that we saw before, not using the swept angle illumination completely destroys the depth reconstruction. Here is a picture of the optical setup that we built to implement swept angle synthetic wavelength interferometry with the lasers, the swept angle illumination, and the rest of the interferometer. With this, I will hand it off to Florian. Thanks for your attention.
Okay, so hi again, everybody. So now I will talk a little bit about how we can use synthetic wavelengths to do non-line of sight imaging. So what is non-line of sight imaging? In our definition, non-line of sight imaging is basically an umbrella term for imaging around corners, but also for imaging through scattering media. So if you would have an optical sensor, for example, that could look around corners, then, for example, you could detect obscured objects on curvy streets, or you also could build some kind of optical endoscope to detect defects. And these are only a few examples, of course, but basically what we want to do here on the left side is we want to turn walls into mirrors. And for future applications of imaging through scattering media, here, for examples, like some examples might be to observe the beating heart through the breast, or to look at brain vessels directly through the skull, and all of this only with optical light in or close to the visible spectrum. And interestingly, the two sides that you see here, they share exactly or very similar problems, because in both scenarios, we have light that is completely scattered in all directions, and this completely destroys the spatial structure of the light. And what people do to retrieve some information about the objects or the hidden scene is basically they look at the time of flight that the light travels. Here, for example, from the source to the wall, to the object, to the wall, and then back to the detector. And in order to do this with high precision, you need a very precise time of flight sensor, which means, again, that conventional time of flight cameras are potentially not precise enough for some applications in medical imaging or industrial inspection, for example. And what we are doing in my group and with our collaborators is we are using synthetic wavelengths or synthetic waves for non-line of sight imaging. And the concept is like very, very similar to what we have seen before. The only difference is that there is now a scattering medium between our sensor and the object. And this can be now solved by going from synthetic wavelengths interferometry to synthetic wavelengths holography. And I will explain you now how this works. So this works by shining light at the two wavelengths towards the scatterer. And in this case, it's very general. So the scatterer can be a wall, the scatterer can be a cloud, it can be tissue. It does not really matter here if the scattering is happening in transmission or in reflection. And then the light is scattered. we have two speckle patterns that illuminate the object, and then the rough object surface creates another speckle pattern that again hits the scatterer. And then after the last scattering process, we have these two completely scrambled wavefronts with an aberration psi that is actually much, much larger than one optical wavelength. And then, as before, we capture again the two speckle fields at the two optical wavelengths. And then again, we calculate the correlation term that I have just described. And now we end up with a hologram of the hidden object at the synthetic wavelengths. And again, the phase of the synthetic wavelengths hologram actually does show a clear structure and is not speckled. And what we do now is we simply perform a numerical holographic backpropagation at the synthetic wavelengths. And by that, we can obtain a reconstruction of our object. And we did this here for the looking around corners geometry, where we project a laser on the wall, and then we image the returned latent field here from the hidden object with a camera. And by that, we can record this synthetic wavelengths hologram that I mentioned directly on the wall, and then eventually backpropagate it into an image of this very small cutout letter N here. And this is how the results look like for this. This is again captured at different synthetic wavelengths. So here you see the captured phase maps of the synthetic holograms on the top, and you can see the reconstructions on the bottom. And what is so fascinating to see here actually is that the synthetic wave again behaves much like an optical wave. And what I mean by this is that the resolution gets better with decreasing synthetic wavelengths, but also you see that the measurements at smaller synthetic wavelengths, they are more susceptible to this degradation that we see here. And this is caused by spectral decorrelation of the two speckle fields, and it actually turns out that these are indeed synthetic speckle, what we see here. So speckle at the synthetic wavelengths. And after doing some calculation, we can surprisingly, or maybe not so surprisingly, find that the limit for this is exactly the same limit, or is exactly this lambda over 4 limit that I have introduced before, but now for the synthetic wavelengths and not for the optical wavelengths. And again, the synthetic wavelengths is of course much larger than the optical wavelengths, and because of this, it can tolerate much more severe scattering. Unfortunately, the time is a little bit too short to go into detail here, and I need to direct you to this paper here for details, but we can use this limit now to formulate a fundamental space bandwidth limit for non-line of sight imaging. And the gag is now because of the tunability of our synthetic wavelengths. For stronger and weaker scattering scenarios, we can always approach this limit very close. And this can be nicely shown in the next experiment. So here we image through scattering media in a transmissive setup. So now the object is this small cutout letter U here, which is hidden behind two scatterers. And in this experiment, we image first through a ground glass diffuser. And in another experiment, we image through a milky plastic slab, which is basically comparable to one of these cutting boards where you cut your onions on. And you basically see in this image that the information, the visual information of this checkerboard pattern behind is already completely scattered out by this milky plastic slab. But nevertheless, we are able to nicely detect the object through the scatterer here. As expected, the milky plastic leads to larger wavefront aberrations, and this means that these measurements here, they deteriorate a little bit faster. And for this specific measurement here through the diffuser on the top right, it's actually very interesting because you can calculate now that this is actually very close to the absolute space bandwidth limit that I have briefly introduced before. And it has also been shown that we reach sub-millimeter resolution for this measurement. Yeah. And the last thing I actually would like to just very briefly talk about today is, because Alankar already talked a little bit about it, is what happens now if we not only use one synthetic wavelength, but if we make a computational superposition of many synthetic fields at many synthetic wavelengths. And what we are doing here is, in fact, we are shaping a synthetic pulse now, which is precisely sectioning the hidden volume. And this can give us, in return, a much better longitudinal resolution of our backpropagation. And here in this animation here, you actually see the pulse distance here if you look very closely. And this becomes now very interesting because now we are entering a regime where we see similarities to light-in-flight imaging, transient imaging, OCT, as we have seen before, and white light interferometry. And this is like very interesting because the circle closes here a little bit. Okay, that's it from my side. I'm looking forward to the questions later, and now I give it back to Ioannis.
All right, so I'll continue along the last part of the talk that Florian already started, which is discussing some computational imaging applications of interferometric imaging. So Florian just alluded to this idea of transient imaging, light-in-flight imaging. So in 2013, Andreas Welten, Ramesh Raskar, and their colleagues, they presented here at SIGGRAPH a paper showing this like super cool video that effectively looks like a video that has a frame rate that's fast enough to allow you to visualize how a pulse of light is traveling through a scene. And they dubbed this transient imaging or light-in-flight imaging. So what's happening here is that if you look at a regular scene of this, regular photo of this scene, a steady-state photo of this scene, it comprises a lot of different light paths that start from the light and from the camera. Like I can draw here a few different paths, some that reflect at the back of this soda bottle, some of them scatter in between, some reach all the way to the front and so on. So what we do in transient imaging is instead of summing up all of these paths into one, we can break them down into a sequence of frames, all of which aggregate contributions only of light paths that accumulate only of light that have traveled in the scene for a very specific length, or in other words, for a very specific time. So this decomposition of steady state into images with contributions from light for just specific path length is what we call transient imaging or light-in-flight. There are a lot of technologies for doing this. Andreas Welten's work was using streak cameras. There have been spot-based cameras, LiDAR kinds of systems, even holographic techniques like Florian showed earlier. One nice way to do this kind of capability is using optical coherence tomography or interferometry with broadband light like what Alankar introduced earlier. And in fact, the nice thing about doing transient imaging using optical coherence tomography is that this gives us very high resolution. We can effectively do this separation at temporal resolutions that are close to 10 to the minus 15 seconds, or in terms of frame rate, that's analogous to quadrillion frames per second. So I'll show you some examples of what this looks like for different scenes, which I think help highlight this kind of resolution. So this is a scene of a gummy bear placed between two diffusers, and the video at the top right is the quadrillion FPS video of this scene. And what you see as this plays is that first there is light, some sharp light, which are the surface reflections, the light that reflects the very front surface of this object. Then there is light that creates caustics inside because of scattering, refraction, and so on. And at the very end, you see this glowing of the gummy bear because of the high order scattering paths. Here are a few more examples. This is a chestnut placed next to a mirror. In this case, what you see in the quadrillion frame per second video is the different reflections we have. So reflections, both primary, secondary, and retro reflections. A scene with subsurface scattering. So in this case, we have a small plate that has both diffused glass and a very scattering material. And as we play the sequence of the transient video, what we see is the different
time that light spends at different parts because of the either just surface reflections or of the subsurface scattering. And lastly, one video I particularly like is a video that showcases dispersion, the fact that light travels inside different materials with different speeds. So what this means is that if we have a very high temporal resolution camera that lets us resolve these different speeds, we can start seeing rainbows in time. Effectively, the fact that red light will come out first, then green, then blue, exactly because of this effect. And this is what this kind of video here is showing. Because we have quadrillion frames per second, then the -15 temporal resolution, we can actually visualize these effects. Now, what can we do with these kinds of very high resolution transient imaging or light in flight visualizations besides put together videos? We've already mentioned several medical imaging applications, tissue imaging, retinal imaging, Alankar showed a few, and so on. I'll get back to this problem of non-line of sight imaging to show you a slightly different spin on it than what Florian discussed earlier. Again, we are looking to image an object that's not directly visible to the camera, for example, because of some occluder. We are trying to do so through some other intermediate surface, let's say a wall, a diffuse wall, that normally would look like it would be completely uninformative about what's lying on the other object. But we can, in this completely uninformative image, there is still some light coming from the non-line of sight object. For example, there will be light that reflects on the wall, reflects on the visible object, comes back to the wall, and then comes back to the camera. So what we want to do is separate this light and then process it in some way that will allow us to do a reconstruction. How can we do that? So most commonly, there has been a long line of works along this problem. Most of them try to use effectively LiDAR-style setups to try and separate the direct light and the non-line of sight light based on path length. So here is how this works. I have my scene. I have, let's say, a single pixel LiDAR. And what this will give me will be a transient, a measurement of photon returns as a function of path length. Now, if I look at these photon returns, there will be a very strong signal at the front, which is the scene that's directly visible to the LiDAR. And through very simple processing of this signal, just basically extracting the max of it, I can do a 3D reconstruction of the scene that's immediately in front of me. But then if I look at the back of the transient, there is this hidden, very, very weak, but present signal that corresponds to all of the light that's coming from the non-visible scene. So if I have a time-of-flight system, I can separate this direct and non-line of sight signal. And then it turns out that from the non-line of sight signal, I can apply a lot of algorithms to do a reconstruction of the invisible scene. Florian mentioned a few, either holographic algorithms or back projection algorithms. There are also algorithms that operate remarkably similar to how reconstruct the visible scene. Basically, they just detect the location of the maximum of this indirect light, this tau NLOS signal I mentioned there. And just by reasoning about this location, we can directly map them to 3D shape about the invisible scene. Now, there are, as I mentioned, a lot of works that showcase this kind of capability with the different algorithms I mentioned for room scale scenes, for object scale scenes. But what we want to see is whether we can do the same for scenes that are now at the micron scale resolution. And it turns out that if we replace the LiDAR-style system with an optical coherence tomography transient imager, like the one I showed you earlier, we can actually solve this problem. We don't need to come up with new algorithms for this, because the kind of data that we'll measure ultimately from the optical coherent tomography system is exactly the same as the one the LiDAR system would give us, albeit at much higher resolution. And then we can take the existing algorithms from LiDARs and just apply them to this case to do a reconstruction that is the one showing here. So here we take a quarter coin, we place it at a part that is not directly visible to the OCT system, to the full field OCT system, and you can see on the right the reconstruction we obtain. It's not as perfect as the one in the line of sight case, but it's still detailed enough that we can see like the outline of George Washington's head, read out some of the details, and so on. In fact, we can go and quantify here by comparing the ground truth LOS scan with an non-line of sight imaging scan, the comparisons between the two, and see that we can actually do this non-line of sight imaging reconstruction at a resolution in the order of 10 micrometers. Okay? All right. So the last thing I wanted to show is that a lot of what we have shown today Alankar, Florian, and I, is about systems that are generally kind of hard to deploy. They can be pretty large, they can be optical table sized, and not only that, they have to work inside an optical lab, in a dark room, in an optical table. I don't know if you ever used this fancy table that floats, it's really on air, so that you can remove all vibrations in the room. So this may suggest that a lot of what we are showing today is not actually super practical for everyday use. So to counter that, I'll show you an example where we actually go against all of these limitations. So we take a system that we run outdoors without any optical table, like exposed in ambient light, everything. In fact, we don't even need to use a special laser. So we call this sunlight interferometry. And here is what's happening here. So Alankar mentioned earlier interferometric designs, interferometric systems that use partially coherent light. What does this mean? It basically means light that is broadband, it's not monochromatic, and light that is also spatially incoherent. It doesn't come from a point source, it comes from an area emitter. Well, it turns out that sun is a perfectly great source of partially coherent light. It's broadband, and it comes from an area emitter. Granted, this area emitter is huge, but from our perspective, which is an astronomical unit away from the sun, this is actually a pretty small area emitter. So as far as we are concerned, sunlight is equivalent from the point of view of coherence properties to the light emitted by an LED, a white LED. So then what can we do? We can take our optical coherence tomography system and get rid of the illumination arm and replace it with a sun tracker. We do need a tracker because the sun actually moves remarkably fast. Like if you take a couple of photos a few seconds apart, you will see that the sun can move, I think, by about a degree. Alankar can correct me here about the exact number. But we place a sun tracker. It's actually something pretty easy to do to put a sun tracker. And then we grab light directly from the sun, we throw it into our scene. And then we can use that to replicate a lot of the capabilities we've shown you for OCT, like 3D scanning, tomography, no line of sight imaging, and do all of them now outdoors and completely passively. No need for a laser, no need for any active light source, just sunlight. So this is a video of what this looks like. We have a scene here. This is a French euro coin. At the bottom left, what you see is the set of images we capture. It may look like these images are all the same, but this is actually a video. There are very, very, very slight variations, which is exactly the extra speckle signal that we have because of interference. If we process those, and the processing here is very simple, we just need to do some spatiotemporal filtering, we end up with a video like the one that's at the bottom right, which is basically the same kind of transient video I was showing you earlier, the light in flight video. And not only that, but just running a simple maximum operation along this video, we can also get a depth map, a micrometer scale depth map of this scene. Again, all of this is happening passively, outdoors, no optical tables or anything. So this is our setup. This is the setup that Alankar put together. He used to run it outside like our office building at CMU. It's like an optical coherence tomography system, except that it's pointing to the sun. And just to showcase that this system is actually robust enough to be able to use, so that we can use it in the wild, in very uncontrolled conditions, we'll be doing experiments at very noisy parts of the campus. So this is a place where there are trains passing by, there is like a parking nearby, so a lot of cars are coming by all of the time, there is an annoying exhaust fan that's making a lot of noise, and there is airflow from there. It's generally a very, very noisy environment, even for standard imaging experiments that are not interferometric. So under these conditions, we can replicate a lot of the stuff I've shown you and Alankar has shown you earlier. So 3D sensing in high resolution, all of these results, again, passive outdoors, where we take a Raspberry Pi and we can capture a depth image like that, where you can even see details such as the conducting tracks on it. Transient imaging, so these are a few transient imaging examples from which we can also extract depth. In this case, the French coin I was showing earlier. Some diffuse peel, where we can also see a lot of subsurface scattering in the transient image. Or another chocolate example, where again we can see the different heights over here, the first and second reflections, subsurface scattering, and so on. So same kind of light in flight principle as before, all passive and outdoors. And lastly, we can also do non-line of sight imaging. In this case, I'll show you an example where we're doing not looking around the corners, but imaging through occluders, imaging through scattering, like what Florian mentioned earlier. So we scan the same scene in direct imaging or in occluded imaging, and in both cases, we can produce depth, and the non-line of sight imaging depth, the occluded depth to reconstruct is very high quality, very close to the one we'd get without any occlusion, and also produce a clean descattered image. Again, all of this is done passively, no active illumination, no laser illumination, completely outdoors, no dark room or optical table. All right? So if you are concerned about many of these systems not working outside of the lab, they actually do. So you should start looking into them and investigating, as Florian said, whether they fit your application case and whether you would benefit from some of them. All right, so that brings us at the end of our course. We've gone over some introduction to interferometry with different light sources, two-wavelength, partially coherent, and computational imaging. Now, before we finish, since we're at SIGGRAPH, graphics and rendering in particular, I wanted to throw out a note about something. So everything we've talked about today has been basically about using in smart ways, or anyway, in useful ways, the fact that light can be coherent, right? So if I look at an image of this object here under regular light, room light, I would see an image like this. But if I look at the same image under coherent light or interferometric, I would see all of this noise that, as Florian mentioned earlier, is speckle. And this noise is useful. I can use that to produce a depth map out of this object. The problem, or a problem that may be relevant to SIGGRAPH, is that all of these coherent effects are things that we don't yet have great algorithms to simulate, okay? So if I go to the rendering sessions, and we have a few of them here at SIGGRAPH, all of the images I will see will be something like the bottom left, smooth images corresponding to images which are under incoherent light. So it would be awesome if we could start being able to render this kind of speckle effects and coherent effects, especially for general scenes. Now, there has been some progress to this end. So, for example, together with my colleagues at the Technion, we had a few papers on simulating speckle. In fact, speckle is not the only coherent effect. There are a few other coherence effects like thin film interference, diffraction, and so on. And again, there has been some work in this area trying to replicate these effects, like by Shlomi Steinberg, or before that by Ramesh Raskar and some of his students. But still, despite these advances, where rendering is with respect to coherent effects is well behind than where it is for incoherent light. And in particular, in the context of this course, we still don't have rendering algorithms that can simulate any of the imaging systems we showed you today, or at least not for general scenes. I cannot take a Mitsuba scene or a Blender scene or a PBRT scene, put not a camera but an interferometer and simulate it. It would be really awesome if we could. So if you're working rendering and you're looking for problems to work with, this is one to explore. And reasons why it would be really awesome to do that is because then we'd be able to use these rendering algorithms to explore this very rich design space of optics and algorithms we have for interferometers that both Florian and Alankar and myself have alluded to. And this would make it a lot easier for us to start discovering new systems, iterating between different designs. We would be able to do all of that in simulation rather than through very tedious and very painstaking lab experiments. So just to throw a plug here, we actually did a tutorial at CVPR where we showed a lot of examples of how rendering has been very useful for computational imaging, for designing imaging systems. In that tutorial, something that's completely absent is interferometric imaging applications, and the reason is exactly, as I said, that we don't have rendering algorithms for that. So if you're working in rendering, you're looking for problems to explore, this should be one that I hope we've convinced you is useful and important enough. All right, so before we finish, many thanks to all of our collaborators. A lot of other colleagues have been involved in all of the papers we've presented today. Of course, we need money to do all of this research, so many thanks to all of our sponsors, NSF, DARPA, ONR, Optica, Amazon, and the Sloan Foundation. And with that, we can finish. Thank you all for your attention, and if you have any questions, we'll be happy to answer them.
Simon Lee from UCSD. I guess I'll take the bait of the last question. So what's the main challenge of simulating an interferometer?
So I would say that we need to, first of all, be able to handle very different coherence properties for light, all the way from fully coherent to very partially incoherent, something that we don't yet have algorithms for doing. Also, we need to be able to, like if we really want to explore imaging, we need to be able to model very different surfaces, from very specular to glossy to rough to scattering. And we don't even have great models for all of that yet, like our BRDFs and scattering sort of generalized, but not quite. And then you also need to have a renderer that can model, I guess, both the intensity and the interference. And you could potentially do that in two passes, like a separate incoherent rendering and a separate interference rendering, but that would not still be super great. So yeah, we have some tools of this, but we don't have the whole pipeline so we can do all of what I'm describing here.
And we need to make them differentiable.
Yeah, ideally, of course.
Hey, this is Akshat from RISE. Great talks. So you talked about at one end there is broadband light source which gives you a pulsed interferometric response, and at the other end there are like two discrete wavelengths, and then you get the beat frequency. I wonder like if there's like sort of space in between, like, and how can you sort of design like, let's say, a bunch of discrete wavelengths and then get any desired interferometric response?
That's probably a question. It's probably a question for me. Yeah, there are,
yeah.
Can you hear me?
Yeah.
There are actually many ways how you can do this, because so you can, for example, pick your frequencies or your wavelengths very wisely, right? How you can do this, and then there's actually a Fourier relation between the different wavelengths that you pick, or the frequencies, and the response that you get. So there's a lot of trade-off space. What I showed today, or what we showed today, was basically only simulating or synthesizing a pulse, but you can actually do much more if you pick your wavelengths wisely.
Thank you.
Hi, can you hear me? This is Talha from Wisconsin-Madison. I had a question on, like, you're getting these really nice resolution in the reconstructions, but do you have limited like field of view issues? Especially for I saw a coin and I saw like this hue which was like pretty small.
So right now, the way that we have built our interferometric setups, yes, we could just put a lens and increase our field of view. That is one thing that we could do. But it turns out that speckle, the fine spatial variation that Florian had mentioned before, may become subpixel if we do that and get blurred out. So that effectively decreases our interference SNR. That is a problem that we face to make them more than centimeter scale.
So if you increase the resolution, or if you increase the field of view, you lose resolution, is that correct?
Yes.
Okay.
I came in toward the end, and you made the claim that there are no algorithms or general purpose algorithms that will handle the general case. Is this that it's an intractable problem in terms of computation? So that's part one. Part two is, would quantum computing, is there a known path to get quantum computing to help? And if so, would this be quantum computing with error correction, or maybe without error correction? Thank you.
So I don't think it's an intractable problem. The fact that we already have some algorithms that can deal with some of these effects in isolation, like just speckle, fully coherent speckle, or just partially coherent diffraction, I think suggests that we should be able to do the same kind of, we should be able to deal with the whole thing, just using ray tracing style calculation. So I don't think we need to go into quantum computing. Now, I think that answers your second question. I'll also say I don't really know too much about quantum